Welcome to the deep dive. So, there's been so much buzz about AI agents, hasn't there? This idea of the year of
Oh,
agents.
yeah, absolutely. But Andrej Karpathy, who's been in the trenches for, 15 years, he has a slightly more, let's say, grounded perspective.
Exactly. He's pushing back, talking
Yeah.
about the decade of agents, and that's what we want to dig into today.
Yeah.
Why? What are the real technical hurdles?
Right. It's about tempering that massive optimism with a dose of engineering reality. Karpathy says the goal for an agent should be like hiring an employee, maybe an intern.
Okay, like someone you can trust with tasks.
Exactly. But the reason we don't just do that today, even with these amazing demos,
Yeah.
is because fundamentally they just don't work yet. Not reliably enough for that kind of trust. They're still very early stage, impressive, yes, but fragile.
Okay, so let's break that down. What are the specific things holding them back? Why the decade-long wait?
He basically lists four major bottlenecks. They feel solvable, tractable, but definitely difficult.
All right, number one.
First is just, well, a lack of sufficient intelligence. They still struggle with complex reasoning, novel problems. They make mistakes you wouldn't expect.
Okay, makes sense. What's next?
They're not multimodal enough. Integrating vision, sound, text, all that data seamlessly. Still a big challenge.
Right, so they can't really perceive the world like we do yet.
Not fluidly, no. Third is the inability to use computers reliably. Browsing, clicking buttons, using software.
Yeah.
It's surprisingly brittle.
Huh. You'd think that would be easier. And the last one. You said four.
The fourth, and this one feels really fundamental, is continual learning.
Meaning.
Meaning you can't just tell a current LLM something new, some fact or instruction, and expect it to truly learn it, to integrate it permanently. They kind of forget.
So you have to keep reminding them in the context window or something.
Pretty much. Fixing these four, yeah, that feels like a decade's worth of hard research and engineering.
Okay. Now, thinking about history, AI has had these sudden shifts, right? But Garbethy points out there was a kind of misstep on the road to agents.
Yeah, he talks about it in historical buckets.
Yeah.
You had early deep learning, Hinton and others, kind of niche, leading to AlexNet training networks for specific tasks. That was the first wave, roughly.
Yeah.
But then came the misstep around 2013, the big push into reinforcement learning on games. Think Atari, AlphaGo later, but starting with simpler stuff.
Trying to get agents to perceive, act, get rewards, the whole loop.
Exactly, the full agent dream. But it was just too soon.
By too soon. Not enough compute? Or something else?
It was more about the approach. We didn't have the representation power yet. The underlying network wasn't smart enough to make good use of those RL reward signals.
Ah, so you needed the powerful base model first.
Precisely. You needed the LLM era, massive pre-training and scale to build that foundation. Then you can effectively teach it complex behaviors with RL or other methods. People were trying to build a roof before the foundation was solid.
That makes a lot of sense. Build the brain, then teach it skills. Okay, so let's talk about this brain, the LLM itself. Karpathy uses this really interesting analogy. We're building ghosts or spirits, not animals.
Right. It's a cool way to put it. Think about biological evolution, billions of years optimizing. You get animals with amazing baked-in abilities. A zebra runs almost immediately after birth, right?
Yeah, it's incredible.
LLMs aren't like that at all. They're pure digital constructs. They learn everything by mimicking human text data from the internet. It's a completely different kind of intelligence, starting from a very unnatural place.
And our method for creating them, pre-training, he calls it, crappy evolution.
Yeah. It's like the best version of evolution we can practically engineer right now with computers and data.
Okay.
And this pre-training process, it does two things at once. One, it vacuums up tons of knowledge, facts, trivia from the web.
Which seems like a good thing.
Well, yes and no. Because the second thing it does is bootstrap the actual algorithms for intelligence. The ability to reason, to learn in context, the problem-solving patterns.
And the knowledge part can sometimes get in the way. You mentioned that might be a bug.
Exactly. It's counterintuitive. All that stored knowledge can actually make the model less flexible, potentially restricting it. The big research goal becomes figuring out how to remove or separate out that vast, hazy memory.
To isolate the pure intelligence.
Yes, to get down to the cognitive core, just the algorithms for thinking, stripped of all the pre-learned facts. It's a wild idea, delete memory to make it smarter.
Wow. Okay, let's dig into that more. How does this ghost intelligence handle learning and memory right now? What are the flaws today?
Well, think of memory in two layers. There's the long-term stuff, everything learned during pre-training. That's maybe 15 trillion tokens of data,
Huge amount.
but it gets compressed massively into the model weight, so it's really just a hazy recollection, like trying to remember details from years ago.
Okay, blurry long-term memory. What about short-term?
That's the context window. Anything you put in their instructions, a document goes into the KV cache. That's like its working memory. It's directly accessible, sharp, and ready to use.
Which is why prompting works so well. You're loading up the working memory.
Exactly. But now, the learning part, the refinement, Karpathy is pretty blunt about reinforcement learning, RL. He calls it terrible.
Terrible. But isn't that how they fine-tune these models, make them follow instructions better?
It is, but the way it works is fundamentally flawed, or at least incredibly inefficient right now.
How so?
Okay, imagine the model takes, say, 200 steps generating tokens to solve a coding problem. It finally gets the right answer. RL gives it a reward.
Good.
But that single reward signal gets applied, basically smeared, across all 200 of those steps.
Wait, even the steps that might have been wrong turns or inefficient?
Exactly. Even if it went down a bad path for 50 steps then corrected, those bad steps still get a little bit of positive reinforcement just because the final outcome was good.
Oof. Okay, I see the problem.
Yeah. It's like Karpathy says, you're sucking supervision through a straw, trying to teach incredibly complex behavior with this one tiny noisy signal at the very end.
So if that final reward is so messy, why not reward progress along the way, like automated process supervision? Give it points for good steps.
People are definitely trying that. It's a major research area, but automating it reliably is hard.
Why? Couldn't you just use another powerful LLM to judge the steps?
That's the common approach, using an LLM as a judge, but the judges themselves can be gamed.
Gamed how? Like tricked?
Yeah. You can often find weird adversarial inputs that fool the judge model. Karpathy gives this example where a model might output total gibberish, like DH, 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 DH.
Random letters.
Random jumps. And a flawed LLM judge, maybe because it's so outside its training distribution, might mistakenly give that gibberish a perfect score.
Oh no, so you end up rewarding nonsense.
You potentially train the model to do useless or even harmful things because the judge was easily fooled.
Okay, that's a serious issue, and that seems like it connects to another big problem. Model collapse.
It definitely does. The models can become silently collapsed. They end up operating on this very narrow set of possibilities, a tiny manifold of thought.
Like they only know 3 jokes, or they always answer questions in the same kind of style.
Exactly like that. And the danger is if you then train the next generation of models on the output of these collapsed models.
It gets even worse. The collapse deepens.
Precisely. The model just keeps getting more and more narrow, less creative, less robust.
How do humans avoid this? We learn from each other, from potentially collapsed adults sometimes.
We seem to have much higher entropy, especially when we're young. Think about kids learning. They're noisy, random, they try weird things.
Yeah, their thinking is all over the place.
That variation, that willingness to explore off the beaten path, even if it leads to errors, seems crucial for avoiding this kind of cognitive collapse. Adults tend to be a bit more collapsed than kids, you could say.
Okay, so let's connect these problems. The memory issues, the flawed RL, the risk of collapse to the real world. Where does this show up in, say, software engineering? That seems to be where AI is having the biggest impact right now.
Yeah, coding is a great example. Karpathy talks about this autonomy slider. You've got different levels of interaction.
Okay, what are they?
Level 1 is, total rejection, just write everything yourself. Level 2 is the current sweet spot, autocomplete. Think Copilot. The human is the architect, directing things, but the AI handles chunks of the low-level code generation.
Right, fills in the blanks, super useful.
Very useful. Level 3 is the full agent dream, vibe coding. You just tell the agent what you want, it builds it.
And how's that level 3 working out?
It works reasonably well for boilerplate stuff, things the model has seen a million times in its training data. Standard web apps, simple scripts.
But not for complex, unique projects.
Exactly. He used his own NanoChat project as an example. It was intellectually intense, a custom architecture. The agents were, quote, very little help.
Why? What were they doing wrong?
They kept trying to shoehorn in standard solutions they'd seen online, like using PyTorch's default distributed training setup, even though he'd implemented a custom one. They couldn't grasp the specific novel requirements of the project.
They couldn't get out of their pre-trained ruts.
Basically, yes. So AI progress isn't a switch, it's turning up this autonomy slider gradually. Humans have always done this, right? Moving from assembly language to C to Python. We keep abstracting ourselves away from the low-level details. Agents are the next step.
But getting that slider to full autonomy for complex tasks, that sounds hard. He compares it to self-driving cars.
He does, and it's a really good analogy. The safety requirements are critical.
Because a bug in production code can be disastrous. Security flaws, crash it.
Exactly. You need incredibly high reliability, the March of Nines, as it's called in engineering. Getting from 90% reliable to 99% takes effort. Getting to 99.9%, 99.99%, each nine is often as hard as all the previous work combined.
Just like with self-driving, where edge cases are the killer.
Precisely. The cost of failure is too high for anything less than extreme reliability. And achieving that level of safety and robustness, especially for complex tasks, that takes time. That's the decade timeline staring us in the face again.
Okay, let's pivot completely. Forget coding for a minute. Forget agents running tasks. What about the really long-term vision? Karpathy seems very focused on education, this idea of maximizing eurekas per second.
Yeah, this is clearly a passion for him. He sees the ultimate potential of AI not just in automating labor, but in revolutionizing how we learn, building perfect ramps to knowledge.
What does a perfect ramp look like?
He uses the example of learning Korean with a really good one-on-one human tutor. What does that tutor do?
They figure out exactly what I know and don't know. You give me stuff that's not too hard, not too easy.
Exactly. They instantly diagnose your current state and serve you material that keeps you always appropriately challenged. That's the gold standard. LLMs are getting faster, but they can't yet replicate that deep, personalized diagnosis and curriculum generation.
And the long-term vision here is what? If AI takes over most jobs,
Then education shifts. It's not about job training anymore. It becomes about self-betterment. Learning becomes like going to the gym, something you do for personal growth, for health, because it's inherently rewarding and, frankly, desirable. The struggle won't be the learning itself, but maybe just the motivation, which AI could also help solve.
that's a fascinating future. But it brings up a classic problem.
Yeah.
Why are experts, people who know the most, often kind of bad at teaching beginners? The curse of knowledge.
Right, because they've forgotten what it's like not to know. They take fundamentals for granted. Karpathy really emphasizes simplification as the key to teaching.
Like his micrograd library.
Exactly. He boiled down backpropagation, this core concept in deep learning, to just 100 lines of Python. Everything else, all the complex libraries like PyTorch or TensorFlow, he argues, is mostly just efficiency layered on top of that core idea.
Teach the core first, then add the complexity.
Yes, and his #1 teaching tip, which I love, is always present the pain before you present a solution.
Make the student struggle with the problem first.
Yeah. Make them feel why they need this new piece of knowledge. Then, when you give them the solution, the eureka moment is much stronger and the learning sticks. Don't just give answers, create the need for the answer first.
That's powerful advice. Okay, so let's try to synthesize all this. We've got this incredible technology, LLMs, that seem almost magical compared to just a few years ago.
Absolutely miraculous in many ways.
But there's this huge gaping chasm between the impressive demos and actually building reliable, trustworthy AI agents that can function like that ideal employee or intern.
That's the core tension, isn't it? We're definitely on this wild, hyper-exponential growth curve in AI capabilities, continuing a trend centuries in the making. But the specific hard engineering and research problems, fixing RL's credit assignment, solving memory limitations, avoiding model collapse, ensuring safety, those aren't magic. That's concerted, focused work.
And that takes time.
Yeah.
A decade feels plausible.
It really does. But the potential payoff on the other side, especially in areas like education, transforming learning from a chore into this pure pursuit of understanding and self-mastery, that's immense.
An incredible goal. All right, to wrap up, here's a final thought for you, building on our discussion. We talked about stripping away all the pre-trained knowledge to isolate that pure algorithm for thought, the cognitive core. Karpathy threw out a number, speculating might still be around 1 billion parameters.
Which sounds surprisingly large, right? For just the core thinking part.
It really does. So the provocative question is, if we truly succeed in isolating and understanding the essence of intelligence, separate from knowledge, how small could that final core actually be? Could pure thought be far more compact than even he guessed?
Ooh, that's a great question to ponder. How much baggage are we carrying?
We'll leave you with that thought. Until next time on The Deep Dive, keep digging deeper.